All right, so we got two more classes before spring break, and then, spring break, and then we come back, and then it's a straight run to the end after that. um, all right, so first thing first, let's see, I am recording, so that's good. So first thing first, the exam is actually surprisingly good. This is the grade distribution. Um, One of the best, distribution I have seen with this class. So I think we are doing pretty good. This is the ABCDF distribution. As you can see, it is completely skewed to A's. Okay, it's not like slightly, it is like skewed, very skewed, which is good. Okay, I don't mind that. And this is the actual plot of the adjusted score. Before adjustment, I think the highest scores were like 3.5-ish. Okay, and it was tied. It was like a three-way tie. I have never seen that before. Okay, so it was a three-way tie to 3.5, and as a result, when I take the third highest score to readjust, no one is getting a whole lot of extra points in this class because the top three people have basically the same score. Um, this is the actual adjusted score, which is actually in your grade book now. Okay, so you can basically use this graph to kind of see where you are in the class. Now, I don't really grade by ranking, okay, but some UC's professors do. Okay, so if you go to one of the highly competitive UCs, those professors would actually assign letter grades based on percentile, which means in a situation like this, the professor would go like, I think A's would be here. B's, we can have a lot. Okay, we can have this many B's. C's, we'll go from here to here, and then D's, and then F's. Okay, I don't do that. I just look at the score. If you are above a certain threshold, you get a certain grade. All right. I think that is I think that's fair, okay? But everybody is entitled to his or her opinions. All right. So do we have any questions about exam 1? You should also have a folder that is now shared with you in which there are three files. Okay, so there's x1 dash and then whatever your ID is, that is your actual paper. Okay, I've scanned everything. If you want to have the actual paper back, I have that too, just not today. The other one is x1k dash and then your student ID. That is the key to your specific exam. And then there's another one, which is I think X1 dash comment. That is the explanation of how you got the score that you get. So those are the three separate files in the folder related to exam one. There will be the same. It will be the same for exam two and also your final exam. If you have any questions, please do not hesitate to ask me. I do want to leave, early today, not like before the class ends, but at about 1:30. But if you want to talk to me about your grade or anything related to this class, usually I am available after class, and I will be available after class on Wednesday for sure. All right. So, any questions? Yep. So the first thing is you want to sign into your W7-digit ID at apps.losrios.edu and then go to your drive, your Google Drive, and then look for things that are shared with you. I suspect you might have received a message as well to your Gmail account. Um, oh, okay, yeah, yeah. So I do everything using your school Google account because I know your ID and I know exactly, how to set up the share. Hmm. All right. Any other questions about this? No questions? All right. So if there are no additional questions, then I am going to close up this tab or just kind of leave it around. And then we'll go back to propositional logic. We do have a homework assignment that is going to be due right after spring break. Okay. So for those people who are thinking, oh, that is not good, I don't want to do anything, that is due immediately after spring break, I have an easy solution. Do it before spring break even starts. That's an easy solution. Get it done by this Friday, and you don't have to worry about, man, I got this thing hanging over my head over the entire spring break. No, that is entirely 100% avoidable. All right, so this homework assignment is about CNF, conjunctive normal form, which we'll be talking about today. So let's go take a look at the homework assignment first. Okay, so there we go. So the CNF homework assignment is asking you to convert a general. Oh, this is not good. Okay, I need to make a slight modification here. It is not wrong. It is just that the notation is not as consistent as I would like it to be. Okay, so I'm going to change the negation symbol from a exclamation point back to the mathematical notation. Okay, there we go. So this is a general Boolean expression, and I need you to turn it into a CNF, a conjunctive normal form, which we'll be talking about. Um, there's also the kind of shorthand version. I prefer the shorthand version myself because it is a whole lot easier to type. Okay, especially when you just use a normal keyboard where you don't have the mathematical symbols. All of the derivations are listed here. Okay, so these are all the derivations that you can use, um, and they should be sufficient for that purpose. All right, so now that you have the homework assignment, and also, it is due on the Monday after spring break at noon, which is right, when the class starts. Okay, so do we have any questions about the setup for the homework assignment? Nope. Okay. All right. So what we'll do is I'm gonna save it, just for that one little notation. All right. So we got a few things to do, but since I just gave you the homework assignment, let's focus on this one, and then we'll talk about some other stuff. So the first thing is, I want you guys to give me a general Boolean expression so I can illustrate how to turn it into CNF. Okay, remember that was kind of one of the things that I asked of you last Wednesday. So did anyone come up with a random Boolean expression using 4 or 5 variables? Okay, well that's fine, and I will show you how you can do just that. You can use Gemini, okay? But you don't have to use Gemini. So what you can do is you can list all the operators that we have. Okay, we have implication, or we have and then we have negation. So let's just say that for this illustration, we want to use 4 variables. Okay, so we got P, Q, R, and S. Okay, so these are the variables, those are the operators. So depending on how complex you want the expression to be, okay, you can make it as complicated as you want it, and you can make it, simple if you want to get a, kind of just get some practice. So I'm gonna go for a medium hard one, okay? So the way to do this, and this is where this class intersects with CISP 430, which is your data structure class, and they started to talk about trees in 430? Not yet. Okay. Okay, so I'm going to talk about trees first. Okay, but in this case, you don't have to implement anything using trees, so don't worry about the actual implementation. I am using a tree to represent the expression. Okay, so the root node, which is the last operation, you guys can now choose. What do you want to be the last operation? Do you want implication or and or not? Pick one. Implication. Okay. So we're going to use implication here, and implication needs 2 operands, or the left-hand side versus the right-hand side. So on each one of the 2 sides, which is what we call a node in the tree, you can now select, okay, what are your choices? If you want this whole thing to be simple, you can just go for one of the variables, which means it is going to be a leaf node in a tree, which basically means it cannot have any sub-branches. On the other hand, if you want this to be complicated, then you can use one of the operators. And If you want it to be like super complicated, you can have operators that require two operands. If you want to exercise just negation, then you can pick a negation. Just choose one. Go ahead. And okay, so we're gonna put and on this side. What about the other side? You want a negation? Okay, so we can do a negation here. So you can see how I am just constructing the tree from the root node. This is called the root node. And I'm just expanding the tree for as deep as you want it to be. Okay, so what about the end over here? What do you want to attach to the end? An implication, okay? Another, okay, well, okay, this might make it a little bit lengthy, but it's okay. We can do that. Okay, so are we ready to go for actual variables now? Okay, so tell me which T and R. We got ST over here. Well, we don't actually have ST, so you want to change this to a Q, S and Q. Yeah, oh, right. Okay, there we go. What about on this side here? What do you want to attach to negation? Hmm? Just R? Okay, that's fine. Okay, so let's say that is our expression. Okay, it is expressed as a tree. So now we have to convert it back into the expression that we normally use, which is called the infix notation. Infix notation means the operator is between the two things normally that it operates on. Now, obviously, we have negation, which is not a binary operator, which means it doesn't have two operands. But that's okay. We just use the operator and then the value in that case. Okay. So to turn this into an expression, there are a few ways to do it. The more intuitive way without explaining what is a depth first search is simply to do the following. We have an implication at the top, so we have some kind of thing implying some kind of thing here. Does that make sense? Okay, now obviously this is a whole lot easier to do on a keyboard with an editor, okay, because you can just insert. So in this case, on the right-hand side, it's fairly easy. It's just the negation of R. What about on the left-hand side? We have a and here, and then on one side of the and, we have P implies R. On the other side, we have S implies Q, and there we go. We have our expression. Is that okay? All right. So that means, since we have four operators and then we have four variables, if you have a four-faced dice, okay, you can actually pretty easily come up with your own Boolean expression for practice purposes. So now the question is, do we actually have four-faced dice? Yep. The, it's yep, yep. It's three triangles with a triangular base, right? Yep. So we do have four-faced dices, and if you're interested, you can, this would be a fun 3D printing project for me, is to print four-faced dices that actually have the four operators on it. Yeah. Okay, I'll think about that. And obviously, I won't sell it, but I'll just kind of bring it to class, and you guys can have fun with it. Okay, cool, cool. But are we understanding the general idea of how to generate some random expression? Okay, so all you need is a random generator. Most calculators has a random generator. Yep. No, because postfix notation is useful, but only um, in certain cases. I forgot one close brand here. So for those of you who are thinking, what is postfix notation? So this is infix notation, where the operator is between the two things it is supposed to operate on. Okay, so the postfix notation. Okay, let's go for prefix notation first. Okay, because prefix most people can actually understand because it's the same thing that you specify function calls or nested function calls. So in a prefix notation, you basically say, what do I want to do? And then you specify what it is supposed to work on. Okay. So then we have this, and then we have this, okay, S, comma, Q, like so. And then the whole thing is ended together. So we have and that is the end. And then on top, we have an implication, which is taking the result of the end and then use the implication here to work out, the negation of or. Negation is already in the prefix notation, so that's the easy one. So this would be the prefix notation, where you specify what you want to do, and then you supply what it is supposed to work on, which is the same thing as how you specify parameters after you specify the name of a function. So prefix notation is pretty easy to understand because we have been using it, already, except in this case, the function name is kind of funky because it's a symbol instead of a name. But other than that, the concept is already well understood. The reason why prefix notation is still pretty natural for us to understand is because it makes use of parentheses. Parentheses are really important because it tells you how things are structured, what is inside what, right? So that is really important. Postfix notation is weird, okay? Because it does not require parentheses, and yet it can express the structure of something like this. So the way postfix works is you specify what first, okay? In fact, the what's, okay? In the case of a two operand operation, you specify the what's, and then you specify what to do, okay? Which is completely opposite to how we specify how things work, okay? Infix notation makes the most sense to us because most natural languages are infix, okay? You have a subject, you have a verb, and then you have the object. Okay. Um, I kick ball. Okay. So you have the two operands, and then you have the operator in between. Um, Prefix notation is still okay because that's how we specify nested function calls. Postfix notation is weird, okay? But it is magical in a certain way. So let me convert this to a postfix notation. You're not required, okay? In this class, you're not required to understand or work with prefix or postfix notation. I'm just going to use infix notation in this class. But I think it is good to have some exposure to all of this. So, 4:30? Oh, that is interesting. Do they do postfix? Cool. So that has to do with how you traverse the tree, because the way you traverse a tree like this, um, how a node represents itself, is it before you traverse the subtrees? Is it between the two subtrees, or is it after the two subtrees? That is the difference between the infix, prefix, and postfix, or inline notation or linear notation. Okay, so I'm going to convert this. So this will be P R imply, S Q imply, and and then we have R not, and then we have another imply. That would be the postfix notation of exactly the same expression. So the way it works is you have to imagine there's a stack of operands, and then you basically sequentially parse the symbols. So once again, this is going back to data structure because a stack is a data structure. It is last in, first out. Okay. So what you do is when you encounter values or variables, you push it on the stack. But as soon as you encounter an operator, you pop the right numbers of items from the stack, operate, and then push the result back on the stack. So that means your PR is going to be pushed on the stack. I got two items on the stack at that point, implies. So I would do the operation, but whatever the result of the implication is now pushed on the stack. So I pop twice and I push once. There's one item on the stack at this point. And then we have S, we have Q. So by the time Q is parsed, we have three items on the stack. The imply here will only pop the last two items, perform the operation, and then push the result of the second implication. So by the time I process the second implication, I will have two items on the stack. And then I encounter the operator and says, I need two things, okay? So it will go to the stack, pop twice, get those two values, perform the conjunction, and then push the result of the conjunction back on the stack. Then I will push R. The negation says I only need one thing. So it's going to pop the R, perform the negation, and then push the negation of R back on the stack. So at that point, I will have the entire result of the N on the stack. I will have the negation of R also on the stack. And then this implication will pop those two items, perform the implication, and then push the final result of this implication back on the stack. So that's how postfix works. Okay, it is very counterintuitive to most people until you kind of practice and use it a lot. If you ask your parents or your grandparents, in some cases, if they're engineers, okay, and you ask, did you have an HP calculator back in those days? And they said yes, then your grandparents or your parents probably know what is RPN or reversed Polish notation, which is one of the names of a postfix notation. All right. So apparently, I just wasted 20 minutes to talk about something that is not related to computer science or this class at all. But that is actually not the case, okay? Because you might think that postfix notation is so weird that nobody is using it, right? I mean, does C++ use postfix notation? No. How about Python? No. What are some of the other programming languages that are really kind of popular these days? Well, yeah, JavaScript, okay, but JavaScript is C-based and C++. Those are basically the same family tree. So Rust, okay, Rust is a good one, but none of those actually use postfix notation. So you go like, this is a useless kind of topic. We don't need to know that. Hmm? Well, in assembly language, only if you take my class. Only if you take my class, you need to know what is a postfix notation. So, but in industry, there's a huge language standard that actually makes use of postfix notation. So, but before I introduce the actual name of that something that you already know, let's talk about PostScript. Okay, if you do not know what is PostScript, that's fine. Okay, it is not something that people talk about a lot these days unless you're shopping for a printer. Okay, most of the time, PostScript is not a name that is recognized by most people because when you go shop for a printer, you want to see whether a printer can talk to your computer. And one of the languages that can talk to your printer is PostScript, and then the other one is called PCL, which is an HP language. So these are the two main languages that your PC can transmit to a printer to tell your printer what to print. Okay, so you look at PostScript. Okay, PostScript obviously is made out of two words, post and script. The post, guess what, refers to post. It refers to postfix notation, and a script means it is a scripting language. It is an actual language. So when you use PostScript to send something to a printer, you are not sending pixels. You are sending loops, conditional statement, functions, and so on and so forth to the printer. The printer says, oh, what do you want me to do? I want you to run that function with these as parameters. And then the function goes like, okay, what am I supposed to do? Go through this loop, and then for each one of these things, do these, da, 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 da. Okay? It is actually a functional programming language. Okay? That's how your printer actually works when your computer sends its instructions. Then you go like, but I don't need to know what the printer is getting in order to print something. Well, this PostScript language evolved into something that is much more prevalent in our daily lives. Okay, so which company came up with PostScript as a language for printers? Nope, it is not Microsoft. Microsoft is a relatively young company. This belongs to something that is older. Nope, it's actually Adobe. And I think before Adobe, and Adobe acquired that from another company that actually made use of PostScript. So Adobe took PostScript and it turned it into that. If you look into a PDF, okay, and I believe PDFs are probably compressed using a zip, algorithm, which means if you rename a PDF into a zip extension, you can actually uncompress it into the actual text content. So you can actually look into the text version of a PDF, and in it you will find postfix notation. So I think this is kind of interesting because it means once you understand all this stuff here, you can make your own PDF. If you find a way to programmatically describe what you want to print, okay, you can write your own program or use AI to write the program so that you can generate your own PDF to specify what you want to print. So I think that is kind of cool. But anyway, that's kind of like how everything relates. Okay, and this is why it is hard for me to stay on track in class because my brain just makes all those extra connections, and I have to keep pruning those branches, and in order for myself to stay on track. And I think most people have no idea how difficult it is for me to choose a branch, to proceed when there are so many branches in my head popping up. It's like fireworks. It's like you have to pick one of the sparkle and go like, let's just follow that one. Okay, cool. Okay, so now we can actually get back to what we are here to do, which is converting that thing into a CNF. All right, so let me use an editor, okay, so that this way I can easily type everything and also illustrate how to use the notation that I think is better than the actual mathematical notation. All righty, so this is just my usual editor, nothing fancy here. And we are going to start a new file so that we don't confuse this with anything else. And I'm just going to use my shorthand notation. P implies R and S implies Q. The whole thing implies not R. Okay, there we go. All right. So in this notation, when you see something that looks like multiplication, which is this thing here seems to be multiplied to this thing over here, it is actually a conjunction. Okay, what looks like multiplication is a conjunction. And then later on, when we see a plus, what looks like an addition is actually disjunction. Okay, so this alternative shorthand operator or expression was something that we also talked about in the first week. Okay, so if you go all the way back to the first module that we talked about in this class, these are the notations that we have kind of touched on, except now we actually make use of those things. All right, so now we want to kind of remember what is a CNF. So if I were to throw a random CNF here, it means you can have disjunctions. A disjunction can have the negation of a variable. It can have a non-negative version of a variable, but then you can only have disjunction of stuff. So you can have something like this, and all of the disjunctions will be ended together, and that's why you have an implicit and over here. So basically, we have an implicit multiplication or conjunction here, except in notation, sometimes I just do not write the multiplication. If you prefer, I can always make the multiplication explicit, just for demonstration purposes. So this way it is easier to read. So I think for this demonstration, I'm just going to make the conjunction explicit by using the multiplication operator to represent, conjunction. So now the question is, how do I convert something like this into something like this? Okay, so we'll go ahead and do this. All right, so I'm gonna do it my way, okay, which is not necessarily your way or the best way. It's just the way that I work on these things. The first thing I do is to get rid of implications, okay, because there are no implications in the CNF. So I know for sure that all of those need to be kind of removed. So when I take care of implication, I just basically look at each implication and say, oh, this is the same thing as the negation of the left-hand side or the right-hand side non-negated. Same thing over here, okay? This is basically the negation of the left-hand side or the right-hand side without negated. And then the same thing over here. So this would become a or, but then I have to remember to negate the left-hand side first. So obviously, having an editor that can help you match parentheses is really helpful because this way you can just land the cursor on one of the two matching parentheses and it will tell you where the other one is. Okay, so I find it to be really helpful. You may or may not, think the same way, but I just think that might actually be helpful. Okay, so the next thing that I do is I use De Morgan's law. So now is a good time to talk about what is De Morgan's law. So De Morgan's law is something like this, okay? If you have A, the negation of A and B, it really is the same thing as the negation of A or the negation of B. All of these rules are already listed in the assignment itself, so you don't have to write it down to remember all of these rules. But if you find writing it down in your notes to be helpful, go ahead and do it. So this is De Morgan's law. To some people, it intuitively makes sense. Okay, the negation of A and B is really the same thing as not A or not B. To some people who are not linguistically oriented, this may not make sense intuitively, which is okay, because how do you prove something like this? Yes, you use a truth table, okay? So how many rows do we have with this particular truth table? Yep, 4 rows, okay? Because we have two independent variables. 2 to the power of 2 is 4, okay? So with a 4-row truth table, you can actually prove this. And even though, that is not something I will put in an exam because it's too easy, it doesn't mean that you would not find it helpful to do it once. Okay, so I do recommend you to kind of use a truth table to prove something like this just once or twice, just so that how that works. So the other way is also true. So there are two De Morgan's laws, okay, or I should say De Morgan's law has two sub-laws. So the other one is saying the negation of A or B is the same thing as not A and not B. So you can see how we just have to flip the and the or, and it works kind of the same. The way that I look at De Morgan's law is I see it as a strange way of distributing negation. Okay, because this is the negation of something that is compound, something that's kind of messy, and this is the distributed version of the negation. The negation is distributed to each component of the original expression, but you have to make sure that whatever the operator was, okay, if it's an and, it becomes an or. If it was an or, it becomes an and. So that's the only part you really have to remember is you have to change the operator itself. That's in De Morgan's law. So I would just ruthlessly apply De Morgan's law until you cannot apply De Morgan's law anymore. Because in CNF, you cannot negate anything other than a variable. You cannot negate an and, you cannot negate a or, you can only negate a variable. So that means every single time you see the negation of an and, you have to distribute that negation in. Every time you see a negation of an or, you have to do the same. So I would just blindly, okay, just blanket the whole thing, keep applying De Morgan's law until it is not applicable anymore. Okay, so that's a general strategy, and I would just kind of do that here. If you're not comfortable with applying De Morgan's law multiple times without the individual steps, that's okay. So we can just go ahead and do this step by step, except in this case, I only need to apply it once. Okay, I was kind of hoping that I have to do it several times, but nope, I only got to do it once. The reason why I only have to do it once is this implication is applied to this end over here, and therefore it matches the pattern of this thing here. Okay, so that means, okay, so I take this negation, I distribute it to every component in the inside of the conjunction, but then I have to remember to turn it into OR. Okay, does everybody see how I just applied the Morgan's law to the conjunction operator, which is this one? I just applied the Morgan's law to that. Basically, it's called an AND because it is the negation of an AND. So as a whole, it is called an AND. If you took CISP 310 from me, you should remember what is NAND, NAND. Okay, so are we doing okay so far? All right. So I just opened up, two more opportunities to apply the Morgan's law. So the two additional opportunities to apply the Morgan's law has to do with this AND, the one that is in blue, is applied to this OR over here. And the same way over here, this negation is applied to this OR over here. So now I can apply the Morgan's law twice, okay, because it's operating on two individual things. So I can just kind of do it at the same time. So I took I took the not on the outside, distribute it to the components in the inside, and then change the operator to an AND. And then the same thing over here, I'm distributing this not into the individual components of the OR, but then I have to change the OR to an AND. So are we doing okay so far in terms of how you apply the Morgan's law? Good. Okay. So just remember, all of these rules are already in the homework assignment, so you don't really kind of have to write it down, but you might want to write down, under what condition do we apply, the Morgan's law, the pattern of how it is applied. So now I look at this one here, okay, and I do encourage you guys to um, derive it step by step, because if you don't do it step by step, you might um, make a mistake, and it would be difficult to spot that mistake later on. So in this case, I look at this and I go like, okay, the negation of P is really just P itself. I perform a simplification. The negation of S is really just S by itself. So um, I can just take that out. So at this point, I have a OR that is nested, and then we have an OR on the outside. So that means we can now apply um, associative law. Okay, so associative law basically means if you have an expression that is an OR and it is ORed with something else, the parentheses can be removed. So this means now I can just do that. Okay, so I take this, and you can see how I'm doing this really, really step by step. One operation at a time. So now we have this, which is exactly the opposite of what I really needed. This is called DNF, or disjunctive normal form. A disjunctive normal form means I have an overall disjunction where each component is a conjunction, and every component inside the conjunction can be a variable or the negation thereof. So I have exactly the opposite. So what am I going to do now? Well, I have distribution. Okay, so Boolean distribution works in both ways. So let me first explain what I mean by that, and then we'll go ahead and apply it. So we have distributive law. So we'll talk about the one that you guys know already. Okay, the one that you already know is A and B, A or B, excuse me, and C is the same thing as A and C or oops, or A and B and C. There we go. Sorry. All right. So this is the distributive law that you already know in normal algebra. Is that correct? Okay. Very good. But it also works the other way in Boolean algebra. So let me give you the other one. So the other one is A and B, the whole thing, or C, is also the same as A or C, the whole thing, and B or C. Now, this obviously is not going to work with integers in normal algebra, but in Boolean algebra, it does work. Okay, so when A, B, and C are all true, false Boolean values, this actually works. So if you say, okay, my mind cannot digest this, okay, because it just looks so weird, I need some convincing, okay? So now we can use a truth table, okay? But this time you have an 8-row truth table because there are 3 independent variables. But the way it works is exactly the same way, okay? You have ABC, okay? You enumerate all the possible true and false value of ABC. You evaluate the left-hand side, okay? Give it a column. You evaluate the right-hand side, you give it a column. Those 2 columns should be identical on every single row. Okay, so I think that's really a useful exercise because from that point on, okay, if you actually do construct the truth table yourself, from that point on, you're not going to look at this and say, oh, it is weird, because you have just proven it yourself in your mind. You just accept it and go like, okay, in Boolean algebra, this works. Okay, and I think that little hurdle of this looks so weird, is really important to get over it, because um, if you don't, then you go like, okay, should I apply that here or not? But once you kind of get over that one, then you can just go ahead and apply it. So now that we understand this, we're going to go back here, and then we basically perform a compound distribute a compound application of the distributive law. So the way that works is you basically look at every single sub-expression and you say, okay, I'm just going to look at every single possible way to pair things up. So I'm going to use the P from here. I'm going to use the S from here. And then I'm going to use the not R from the last portion over here. That's one way, okay? And then you have another one, okay, which is using the same P over here, but this time you pair it with the not Q over here. So we have P or not Q, and we still have the not R on the other side. And then we use the not R from the first one. Basically, it is known as basically FOIL, okay, FOIL in normal algebra, which I cannot remember what that means anymore. What is FOIL? I cannot remember. Okay, okay. What is FOIL in? Oh, in. Okay, that sounds about right. Okay, FOIL is a mnemonic acronym to multiply 2 binomials. Okay, but what does it mean? Where? Oh, second line. Oh, okay. First, outer, inner, last. Okay, there we go. So that's FOIL. Okay, cool. But basically, we are doing exactly the same thing as a coil in this case. Okay, we are basically foiling these two. This one is always just a tag on at the as the last thing. So we have not R or S, and then we have not R or not Q, and I just have to plug in not R over here. Okay, we'll do the simplification later. Okay, but I'm just going to give you the actual result of the FOIL operation. So this is not really just a 2-step FOIL. Okay, this is actually a 3-step FOIL-ish, but that's the result. Okay, do we have any questions about this particular FOIL operation? Okay, it's just that it's not using your usual algebraic, distributive law, which is only this one. But in linear algebra, we have a second one, which is actually applicable in this case. So now we can go for simplification. So the simplification that we're going to use here is basically to say A or A is just A. Okay? Well, does it make sense to you? So once again, this is not a plus, this is an or. Okay? This is A or A is A. So If it intuitively makes sense to you, great, not a problem. Okay. If it doesn't make sense to you, what do you do? A truth table. Okay. But this time, this is a two-row truth table because A can only be true or false. Okay. So you evaluate A or A. Okay. And then just compare that to the value of A on every single row. It should be obvious that these two expressions are the same. Okay. The other one that is also kind of helpful in terms of simplification is A and A is also just A itself. Okay. All right. So now we apply that. Okay, which means not much I can do with the first one, but personally, I like to order things so that it is alphabetically ordered. Okay, but that's just me. It is also going to be helpful in the second part of this homework assignment, which is resolution. So I would just kind of go ahead and sort everything in an alphabetical order. So this one I can simplify to just not R or S, and then this one, whoops, is just not R. Let's see, P, Q, R, S, T. Okay, so this is not Q or not R because I just want everything to be alphabetically sorted. All right, so if you give me this as the answer, or even the previous line, I would give you a perfect score. Okay, if you give me something like this, which is not simplified, but it is a CNF. Okay, because the homework only asked you to give me a CNF. If you give me a CNF, I cannot say, nope, you're not going to get all the points. So that answer alone is going to get all the points. Simplification is helpful, and I think it is just a good thing to do, okay, just to exercise how well you can work with these equations. So as it turns out, we have another simplification here, okay, and this one is really, really weird, okay. This one is called absorption. Okay, this only works in Boolean algebra, by the way. Okay, so absorption means when you have A or B and A. Okay, this whole thing can be simplified to just A. Okay, well, does it make sense to you? Let me ask. So we have A and A or B. Okay, and I claim that if you evaluate this entire thing, B is useless. B is completely useless in the original expression because the whole thing just boils down to A. So with this one, I'm just going to work out the truth table. Okay, so I'll work this one out for you. So we got A, we got B, we got A or B, and then we have A or B and A. Okay, so I'm just going to break it down to four stages here. A can be false, B can be false, then this is going to be false, and this one is going to be false, okay? Because if one side of an AND is false, the whole thing is going to be false. Okay, so we have this will be true, and this will be false, right? And then we have this will be true, and this will be true, and then we have true, true over here, this will be true, and this will also be true. So do you notice how the column for A and the column for A or B, the whole thing and A, they are the same. In Boolean algebra, if the truth table says two expressions are identical for all the rows, that's all you need to prove that the two expressions are the same. Are we good so far? So this is absorption, okay? So absorption is kind of weird because it doesn't work in normal algebra, but what it does allow us to do here is to say, hey, look at this part here. That is the same thing as exactly that thing here. So that means this entire expression here is of no use to me. So if I were to apply absorption, I can now say, yeah, we can take that out entirely. And then you look at the second one, you go like, okay, this part here is really the same thing as this part over here. So now you can take out this expression entirely as well. So that means after simplification, this is the CNF that is as simplified as possible. But you don't have to do the simplification to that point. Okay, so when you need to turn in your homework assignment, you only have to turn in something that is a CNF, a conjunctive normal form. Yep. No, you don't have to sort it in alphabetical order. I personally think it is easier to identify things that I can do if it is kind of alphabetically sorted, but you don't have to. All right. So are we kind of getting a good idea of what you need to do with your homework assignment that is due in 2 weeks minus 50 minutes? I have to be precise, right? Precision is everything. Precision is everything that LLMs cannot do, I should say. Okay. All right. So that is done. Okay. You have 2 weeks to work on this. And once again, if you don't want this homework assignment to ruin your spring break, just get it done before you start on your spring break. You're all good to go. All right. When was the last time you guys did algebra, like in the class? Okay. Yeah, long time. Huh? Well, linear algebra is a kind of algebra, okay, and so is abstract algebra, which is actually quite interesting. I cannot diverge into that today, but it is one of those things where it is actually quite interesting to understand. All right, so with that done, I can now go back to another assignment, which I said is not going to be graded, that I asked you guys to do. So let's go ahead and do that one now. Okay. And let me find out where I stash all that stuff. It's right here. Okay. So question number 5 to number 8 is what we want to do. All right. So question number 5 is a three-hop derivation. Okay. And the one expression that we quote unquote want to prove is S by itself. In other words, S by itself as an expression is quote unquote the theorem. Okay, a theorem is nothing more than a statement that needs to be implied by everything that is known to be true. Okay, I'll say that one more time. Okay, a theorem is a statement that is implied by everything that is known to be true. Okay, so in this case, we are going to use just um, propositional logic to do it. And we only use iota, which are things that are given to me as true. And you can see the constant of 1 is not even in there because it's not needed. And zeta only includes one single transformation in this case, which means choosing which one to use inside zeta is easy because you only have one rule. Okay, so we'll go ahead and start. Okay, I need an expression that is true. I need that single expression that is true already to also be involved as the left-hand side of an implication. So this is now a pattern matching kind of thing, right? So we look at this and go like, well, can I choose one of the implications? The answer is no, okay? Because if I choose one of the implications to be phi, then I have to find an implication that has an implication on the left-hand side, which does not exist in here. So I go like, nope, that won't work. But what if P as an expression is just phi? Can I find implications that has P on the left-hand side? We go like, yep, there's one. Okay. So now we have P basically substituting phi, and then P substituting phi again, and then Q is substituting psi. So now this requirement is satisfied. When that requirement is satisfied, okay, when that pattern is matched, then we infer whatever is on the right-hand side, which is psi by itself. So by combining these two, now Q is proven, okay, or Q is labeled red using the red-blue thing that we did last Wednesday. Okay, but now the Q is by itself known to be true, okay, or proven to be true in this case. We just need it to be true, whether it's from iota or later on we add to the set D is not really that important. So now we have Q, and then we have Q as phi. Q implies R as the second element of the set. We have a match. So now we can put R by itself into the set D, okay? The set D, uppercase D, is the set of well-formed formulae that are true. Okay, It can be from iota, but it can also be proven using something from iota or D itself. So now we have R also being as an expression that is true. R implies S is known to be true in iota. We combine those two, and finally we can produce S as an expression that is true. So that's how it is. It works as a three-step derivation. So now we work with question number 6. Okay, so this one is slightly more complicated because we got two rules in Zeta, and for some reason, the AI decides I don't like to use just phi and psi. I want to use alpha and beta. Okay, fine, you'll use alpha and beta. Okay, so now we look at these two rules, and then we want to know when do we stop. Okay, it says we want to derive t. In other words, we want to use all of these derivations to arrive that t is true. Okay, so let's see how we can do this. Um, All right, so I think the first thing we do is we make use of, we bind P to alpha, we bind Q to beta, okay? So it is a match. This is the only element that is needed in that particular set. So that conjunction is, okay, this conjunction matches the pattern of this conjunction. So we now say, okay, we can now infer that alpha, which is P, is true. Is that okay? So that's how we can derive P as a statement is in D, in the set D. Okay, so once P is in set D, then we can use the other transformation rule twice, because then we can use phi as P, and then we have P implies R, so psi is R. That infers R is true. So now we have R as a result, and then we plug R back to become phi again. This time we have R implies T as the second item in the set. We fire that rule, and then we end up with T being true, and that's how that one works. We do okay so far with how the propositional system works. So this is all about pattern matching. Okay, in other words, the operators actually have no meanings in this case. All we are doing is just pattern matching and throwing some patterns back into the pool so that it can be used again. All right, so let's work with number 7. This is once again a 3-hop derivation. So this time we have 2 items in iota, and then we have what? One, let's see, we got 1, 2, 3 items in zeta. Okay, so what we want to arrive is not P and R is a result. Okay, so for this one, it might be better to kind of write it down. Okay, so let me use uh, this here. So this is working, we are working on number 7. Okay, so let me scroll all this out and then work on question number 7 here. All right, yep. Um, well, these are specifically kind of doctored that way. But Zeta, the full transformation system or the full propositional logic system for humans has 20 something rules. This is way simplified just so that we can get some practice out of it, but it is incomplete. Which means there are certain things that we can actually do by hand. Logically, it makes sense that this cannot derive. Yep. All right. So we're gonna start with not P or Q, and we also have R in D initially. All right. So the first one that we can apply is we have to use exactly something like that. So this is the rule that we can fire first. Okay. So step one, oops, step one, okay, is we look at not P or Q, and then this is going to infer, okay, this infers the negation of P and the negation of Q. You can see how this is, basically De Morgan's law, or one of the components of De Morgan's law. So now we can throw that into D. Okay, so D now also contains the result of that derivation. So now we look at step 2. Okay, we basically have to evaluate what is applicable in this case. So we look at the three transformation rules, okay, and we say, okay, which one is applicable? I think in this case we can use A, alpha, and beta inverse A. Okay, so that one is applicable. So we'll go ahead and apply that. Okay, I'm not sure exactly whether that's going to be helpful or not, but it looks like it's going to be helpful. Okay, so we'll go ahead and apply. I mean, the worst case is if you apply something and it's not really useful, it just puts something into D that is not exactly what you really need, but it doesn't negate the whole process. Okay, you can just go like, oh, I guess that doesn't work. Okay, so we're gonna use that rule. So this time we're gonna specifically say not P, oops, not P and not Q in first alpha. It only infers one side, which is not P. So now we put not Q or not P into the whole thing. Okay. So now we say, okay, what else can we do? The result is not P or R. R is already there, P is already there. Okay, so this one is kind of tricky because we're going to use the last transformation rule. Okay, the last production. It's also called a production. The transformation rule is also called a production. So we're going to use the last production because all it says is give me any two well-formed formulae that are already in D. Okay, and the conjunction of those two should also be labeled. Okay, so now we just go like, oh, okay. That means I can now specify. Okay, this is my third step. Okay, so the third step is we are going to take not P, okay, not P as one of the statements. We're going to take R as the other statement. So this set would be a set of two statements that are both in D at this point. Okay, but that means it infers that not P and R is true, which is exactly what we want. So it's a three-step derivation. Are we still doing okay so far with how to apply, the transformation rules? Okay, so the last one is a four-step process, and what the question wants us to prove is what is it? T is in D. Okay, so we'll go ahead and work on that one. This is number 8. All right, so D is going to start with everything that is in iota. So we have P and Q. Q implies R, not S. Oops, not S implies not R. And then finally, we have S implies T. And now we have to look into the steps. Okay, step 1. Um, let me. Oh, that's the entire. Yep, that's the entire set of zeta. We got 3 rules this time. So we have the conjunction, but this time we are pulling the right-hand side of the conjunction to be the result of the production. We have the usual, okay, we have, rho implies phi, and then that infers phi, which is something we have seen already. Um, and then we have this one, which is kind of like implication, but it works in the opposite way. In other words, it says if we have an implication where it is the left-hand side is the negation of something called phi in this case, the right-hand side is the negation of rho, and we know rho is true, then we also know that phi is true. Okay, so that's how the syntax works out in this case. All right, so looking at this, okay, so I'm just reversing the whole process, and into Q to R. So I think the first one we need to apply is just going to be the conjunction one. Okay, so this one is looking at P and Q. as a set of one single expression, and that infers Q by itself. The second step, okay, is once that we know Q, okay, so we have to put Q into D. So once we know Q by itself is true, then we can work on the second one, okay. So this time we have Q implies R, and then we also know Q is in D at this point. So that infers R is true. So now we can put R in D. Oops, R. There we go. And then the third step is going to be, let's see. Yeah, so we have the we have to make use of this one, okay, which is actually using this particular proposition here or this particular production. So that means that we have not S implies not R, but we know that R is true, so that infers S. And then step four is knowing that S is already true. We have S implies T is also true, so that infers T is true. So that's how the four steps work. Is that okay? All right. So back in the days, okay, the Greek philosophers would basically use the 20 plus rules, okay, and they would, each variable would be something like, a certain emperor sucks, okay, and then another variable would be that country lost the war, and then another variable would be the emperor got assassinated, or something like that, okay, and then they would use propositional logic to basically derive and go like, yep, that makes perfect sense. I mean, do okay so far? Okay, that's propositional logic. Okay, but practiced the human way. Okay, so now that we have, um, I'm thinking about taking row, but I'm on the row here, so I'm not going to take row. Ooh, no pun intended. All right. So what we'll do is we're going back to the lecture notes. Okay, because we are going to just put a little bit focus on proof by contradiction, okay, which is, okay, I'm going to do the lazy thing, go back to the heading here, just go to proof by contradiction, and there we have proof by contradiction. I think we got enough time to prove proof by contradiction, okay? That is actually important, okay? Before you apply a technique, we kind of have to know how does it work. So in this one, I use Boolean algebra to prove that doesn't matter what is P, Q, and R in this case, this implication is always true. Okay? So this is actually not a bad way for you to practice the use of Boolean algebra. Okay? How do I go from one line to the next? Okay, so if you want to get some practice of how to apply Boolean algebra, you can work this one out. Okay, well, it's already worked out. You just have to quote unquote map it. Okay, in other words, how did I go from line one to line two? How did I go from line two to line three, and so on? Okay, because the more you practice, the easier it is for you to understand. Oh, okay, with this pattern, I need to apply that rule. But for our discussion, all we are really interested in is this implication is always true, which is kind of weird, okay? Because what this says is if P implies Q is true, okay? So we are looking not as P being true, not Q being true, but the implication is true, okay? If P implies Q is true, then P and R, the whole thing, implies Q and R also has to be true. But tech, does it matter what R is? The answer is no, it does not depend on what R is. As long as you know P implies Q is true, you can introduce a third expression R, and then it is guaranteed that P and R as the left-hand side, Q and R on the right-hand side of the implication, that implication will also have to be true. Okay? So once again, you can use Boolean algebra like this to prove this implication is always true. You can also use truth table if you want to. Okay, so there are two techniques to prove this particular thing. But this one is not proof by contradiction. It is a corollary, which is a small theorem that we're going to use to prove proof by contradiction itself. All right. So this one is actually proof by contradiction. Okay. So what is it? How does it work? We'll just say that. Let's just say that phi is a theorem of psi. What? What is a theorem again? A theorem is a statement that is implied by things that are already known to be true. That's a statement. So what this is saying is psi is just a placeholder here. Okay. In other words, this one single Greek symbol psi can be this long, representing all the theorems, everything that is known to be true. That's psi. Okay. Things that are given to you that you don't have to prove that it is true. On the other hand, phi is the actual statement, the actual expression that you need to say, is this phi as a statement, which can be as simple as a single letter like PQRST or something like that. So we need to show that this implication is true. That is a proof. Okay, when you're proving something, you're connecting implications from everything that is known to a specific thing that you need to show that it is true, that is implied by everything else that is true. So now I introduce the third expression, making use of the corollary. Okay, the third expression turns out to be not phi. There's no restriction of what the third expression has to be, so I'm just going to say, well, let's just pick not phi as my third expression. So now, because of the corollary, this implication also has to be true. So, but not phi is kind of special because not phi and phi cancel out to become false. Is that okay? So that means phi, excuse me, psi, which is everything that is axiomatic. Okay, these are all the things in iota. If you make a conjunction with the negation of the theorem that you're trying to prove, that conjunction has to lead to false. Are we still doing okay so far? So this is counterintuitive to most people because in order to prove that phi is implied by psi, you negate it first, and then you put it in a conjunction with psi. And then your job is to show that that conjunction is false. Okay? Are we still doing okay so far in terms of understanding the mechanism of proof by contradiction? Okay? All right. So this time, because last time I used my socks as an example already, so this time we're going to use the pigeonhole principle. Okay, the pigeonhole principle is a rather simple statement. It is basically saying what happens when you have an overpopulation of pigeons, and pigeons are always overpopulating. That's why they're called flying rats. Okay, so the idea is we have n pigeons. Okay, n pigeons. We have M pigeonholes. Pigeonholes. Okay. So a pigeonhole is basically a home for a pigeon to stay overnight. Okay. So basically we have N pigeons and then we have M pigeonholes. You are also told that there are more pigeons than there are pigeonholes. So all of these are given. Okay. You don't have to prove these. You just go like, okay, that's the assumption. This is the problem of pigeons overpopulating. Okay. These become your psi. Okay, it becomes everything that is given to you. So what do we want to prove? What is psi? Psi is basically saying, in this case, I know that at least one pigeonhole has has more than one pigeons. At the end of the day, after all the pigeons fly home, at least one pigeonhole is going to have more than one pigeons in it. So intuitively, you go like, yeah, that makes perfect sense. Then I ask, prove it. And you go like, how do I prove something like this? Most people would start with examples, right? So let's say we got three pigeons and there are two holes, and we can have all three pigeons in the same hole. We have two pigeons in one and one pigeon in the other one, blah, 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 blah. Well, yes, okay, you can use it to argue that in the specific case of three pigeons and two pigeonholes, the statement is true. But can you show me that when there are 500 pigeons and 499 pigeonholes, the theorem is still true? Are you going to work through all the possible cases in that case? No, because it's tedious, right? You know intuitively you know it is true, but you cannot just say, yeah, I can enumerate all the possible cases of how the 500 pigeons will occupy the 499 pigeonholes. People would think, yeah, but there are only like 499 cases, right? You know, because every pigeonhole would be filled up with one pigeon and only one of them has two pigeons. No, you can have all the possible cases of, well, maybe one single pigeonhole has all 500 pigeons. So you have a huge number of cases to prove, okay, which is not the best way of proving something like this. So the way this works, okay, is to negate phi first, okay? So when you negate phi in this case, you're basically saying we're negating this, okay? What is the negation of at least one pigeonhole has more than one pigeons? All pigeonholes have no up to one pigeons, okay? So you say all pigeonholes have at the most uh, one is greater than or equal to. Okay, I'm gonna say at least up to. Okay, up to one pigeon. Okay, that is the negation of phi. Does that make sense? Okay, so now what you need to do is to say if I'm not changing psi, okay, we're still assuming that there are n pigeons, there are m pigeonholes, and there are more pigeons than there are pigeonholes. Yes, go ahead. Mhm. We are trying to prove phi. We are trying to prove that at least one pigeonhole has more than one pigeon. Okay. So now the question is, what can you possibly come up with when you combine psi, which is still the same as before, but this time we are combining the negation of phi using conjunction. Okay. What does that imply? So you look at this and go like, there are only n pigeonholes and oh, excuse me, there are m pigeonholes. Each one can only have up to one pigeon, which means the number of pigeons has to be less than or equal to m. Does that make sense? Mathematically, does that make sense? When you combine psi, okay, which is still saying n is greater than m, and then you combine that with the negation of phi, which is basically saying all pigeonholes can only have up to one single pigeon, then it follows that the total number of pigeons has to be less than or equal to m. Okay, that is phi itself. Psi is n is greater than m. So you end up with this. What does that imply? Well, find me two natural numbers, n and m, such that n is greater than m and n is less than or equal to m. Can you find me two natural numbers that can do this? You cannot, right? So that means when you combine these two things, it is implying false, which is called a contradiction. So we arrive at a contradiction. Most of the time, when people say, you are being contradictory, okay, or your argument has a contradiction, it is not a good thing. But in this case, it's exactly what we want, okay, because of the structure of proof by contradiction. This is actually the great thing that we can come up with. We are basically saying, yep, the pigeonhole principle makes sense. Are we doing okay so far? All right. So, um, proof by contradiction doesn't seem like it's very useful. Okay, it's a great name, right? It's kind of cool as a name. Proof by contradiction sounds cool. Okay, but it's actually really useful in math, especially in computer science when you need to prove theorems in computer science in at least two classes that you have to take as upper division classes. One is called computation theory or automata. The other one is called the analysis of algorithms. Both of those are essentially math classes. Um, this class, by comparison, is only introducing the alphabet that you have to use in those two classes. Okay, but proof by contradiction is super helpful. Later on, we'll also take a look at proof by induction. Okay, so proof by induction is the other algorithm or the other proof technique that is really helpful. I know we are running out of time. There was a software engineer who got interviewed about the curriculum of colleges, like what we should be teaching, what we should not be teaching. And one of the things that this particular engineer, software engineer, said was we should not be teaching recursive algorithms because in real life it is not practical. And I would agree, okay, that in many cases it is not practical. But recursive algorithms and proof by induction are going like this. If you have an algorithm that is expressed recursively, its correctness would be easy to prove using proof by induction. And every recursive algorithm can be transformed into an iterative algorithm and the other way around too. So that means if you can prove an algorithm that is recursive is correct, okay, you can also then prove basically the iterative version of the algorithm also has to be correct. So from that perspective, I would basically say no, recursive algorithms are still important from the perspective of verification, which is basically we are building up the tools, okay, the really basic tools that you need in order to prove something is correct. All right, so we are running out of time. I will not charge you for the 2 extra minutes. I'll see you all on Wednesday.